Okay, so this is video 2 for the Unit 4 practice problem set, and we are on question number 3. Given the quadratic function f of x equals negative 3x squared plus 24x plus 60, let's find the x-intercepts, find the value of the function at 2, and find the average rate of change in the interval 6 to 9. So, as usual, the first thing I need to do is enter the function. Not do that. Let me try that again. Minus 3x squared plus 24x plus 60. And I'm going to do zoom standard again and see how this, how bad or good of a picture I get. Not too bad. It's not good enough, but I can at least see it here and here. I can see the two legs. So I really just need to zoom out and kind of over this way. So we could sort of, actually let me go back to that picture. Let me get some values here. So that's minus 3 approximately. And then over here on the right, it's painfully slow, but actually why don't we just count? That's 10, so let's go up a little higher. Let's go to like 15. So let's go from minus 5 to 15, and then I'll do zoom fit with that. Okay, better. Now I can see my two intercepts. I have one here and one here. So to find my intercepts, those are zeros. So let's go to Calc 0. Where's my cursor? It's up at the top. So let me move it to where you can see it. And so now I'm on the left of that 0. And now I want to go to the right, so I hit enter again once I'm on the right. And now I'm going to move down to a guess. And negative 2. Okay. Now there's another one over here, but I'm going to let you find that one on your own. It's exactly the same process, and you have the answer at the end of this document. So you do Calc 0 again, but do left bound here and right bound over here. All right, let's move on to part B, f of 2. So there we want to evaluate the function. So that's vars, y vars, y. Now notice here I made a mistake. I forgot to exit the screen. So let me make sure you actually exit the screen. Evaluate the function at 2, and we get 96. Okay. Part C, find the function's average rate of change in the interval 6 to 9. So for this one, I'm going to, there's a couple of ways to do this, but I'm going to do it like this. I'm going to do y1 of 9 minus y1 of 6 over 3, because that's 9 minus 6. So this is the function. What I'm using here is f of b minus f of a over b minus a. That's the average rate of change formula. I could do this using delta list, but that's sort of overkill since I'm only doing one. So okay. So vars, y vars, function y1, and that's at 9. And I'm putting, notice I put a parentheses first, because I want to do this whole thing in parentheses so I can find the numerator, which means I need another parentheses. And you don't have to do it this way, but this way I can do it all in one step. And then I divide it by 3, and I get negative 21. Okay. So that takes care of question number 3. Let's move on to number 4. Pictured is the graph of an nth degree polynomial function and includes all of the function's turning points. Okay, so true or false, the range of the function is negative infinity to positive infinity. I'm going to say that's false, because if this contains all the turning points, then my endpoint behavior is that I am going upwards as I go to the left and to the right, and so this thing's not going back down. So these are this is the bottom of the function right here. One of those two is the smallest value. So it has a minimum. So it does not have it does not go down forever. It has an absolute minimum. So that's false. The range is not all real numbers. Part B, is the degree of the polynomial odd or even? Well, this is going to be an even degree polynomial. And the way that I know that is because, well, when we're studying the classification of polynomials, even degree polynomials are the ones whose endpoint behavior is the same on both ends. In other words, as you go horizontally out, they both go up or they both go down. Another way to think about the evens is that they all kind of start with a quadratic, and then you put a bump in that quadratic, and then you put another bump in that, and you just keep on messing with this quadratic and putting more bumps in it. But they all have this, or they could also do like this too. Right. Okay. So anyway, this is going to be an even one. Part C, what is the smallest possible degree of the polynomial? Okay. So the smallest possible degree of the polynomial, well, let's look at the number of zeros that we have here, because the number of zeros is related to the degree of the polynomial. In fact, equal to. Well, I should be careful when I say that. Let's say this: if the degree of the polynomial is n, it can have at most n zeros. That's the statement. So this guy has 1, 2, 3, 4, 5, 6 zeros. So the smallest possible degree of this would be 6. Okay. Question D, is the leading coefficient of the polynomial positive or negative? Well, it's going to be positive because it opens up. If it was negative, it would look like that, or it had more bumps, but it would, be going downwards. But it's not, it's opening upwards, and so it must have a positive leading coefficient. How many x-intercepts are there? Well, we just counted them, actually. There's 6 of them. How many turning points are there? That's a turning point, that's a turning point, that's a turning point, that's a turning point, and that's a turning point. So 1, 2, 3, 4, 5. Okay, how many inflection points? So every time we change from concave up to concave down, we have an inflection point. So we're just going to have to roughly guesstimate where they are. So we have one in here somewhere, we have one in here, we have one in here, and we have one in here. We do not have one over here, and we don't have one over here because we're not changing concavity. So that's 1, 2, 3, 4 inflection points. Part H, on the far left-hand side of the graph, before the first turning point, so that means like over here, the function is doing what at what kind of rate? Well, it is decreasing. It's going down because remember, we read left to right. So this is going downwards as we move left to right. And it's going downwards at what kind of rate? Well, it's at a decreasing rate. Remember the picture for decreasing at a decreasing rate is this. And that's what we're doing here. Furthermore, the graph itself is concave up in this region. So the region that we're talking about is basically here. Okay, I think that's all for number 4. Oh, no, there's one more. On the far right-hand side of the graph, on the far right-hand side of the graph, so over here, over there the function is increasing, and it's increasing at an increasing rate. It's doing this. And over there we are concave up again. Okay, so that's the last part of question 4. So let's move on to number 5. All right, consider the function f of x equals 8x sine of x. Now this is a kind of a weird one. In this formula, sin is pronounced sine, and that's the trigonometric sine function that's available on your calculator via the sin key. I'll show you right here. Okay, so that's a function. The domain of this function is all real numbers with x measured in radians. I know we don't know anything about this right now, but that's just the unit of measure. So we're gonna, because of this whole radian thing, and I don't worry about this too much, but we have to make sure that the calculator mode is set correctly. So go to mode and make sure that this is right here is in radian and not degree, which it is. This is what I'm talking about. So I want it to be over here in radian right now. Okay, so basically we're just kind of introducing sort of a new function and gonna find some minimums and maximums of this guy. So let's find the minimum value on the interval from 1 to 3 and then the maximum value on the interval from 1 to 3 first to get started. So 1, 2, 3, and then I'll do zoom fit. Okay, actually, let me say something about this before we go any further. Like, what's the point of this question? That's maybe the most important thing. The point of this question is not that you are, primarily that you're learning about the sine function. That's kind of a secondary issue. The main point of this question with all these minimums and maximums is that you understand the idea of finding the minimum and the maximum of a function in two situations. First in the situation when the vertex is present in the picture, and then in also situations where the vertex is not present. So here's what I'm getting at. If I graph this function from negative 15 to 15 as this is talking about, let me actually draw it here for you. If I graph the sine function, let me put that in black. It's gonna look like this. Okay, and well, actually like that. And so negative 15, I don't know, let's just say it's like right here or something. And then positive 15, let's say it's over here. So if we restrict our attention just to like the function within this green box, we've got maxes and mins all over the place. Now, if I say, what's the maximum in here, in this yellow shaded region? Well, in this region, the maximum is right there. And then the minimum what would the minimum be? Well, within the yellow shaded region, that minimum is either going to be this value or this value, whichever one is lower, right? So I don't know. I'm not saying it's both of them. I'm saying it's one or the other. And usually you can visually inspect it and tell. But if I go, let's pick another region. Let's say this is the region that we're looking at. Okay. Now, in this region, what's the maximum? Well, it doesn't include, so I'm talking about from here to here. The maximum is not, like the vertex is not in this interval. So the maximum is just going to be the rightmost value. And the minimum will be the leftmost. But the thing to remember here is that you can't use calc max and calc min here. So in this scenario, you cannot use calc max and calc min. What you do, so let me write that down, you can't use calc max or calc min. What you can do instead is evaluate the function at the endpoints of this interval. So if this was like 3, I would do like y1 of 3. And if this was 5, I'd do y1 of 5. Okay. So whereas here I would use calc max in this other region,